Okay, so yeah, thank you. Welcome to my talk. So, as my talk title says, what I will be talking about and investigating was Paranthropus actually absent from the Afar Depression in Ethiopia, or have we just not found it yet? And so, instead of kind of weaving multiple projects together and kind of unifying them under a broader theme, I'm going to be doing a deep dive into one project. Okay, so the outline for my talk is why the genus Paranthropus. Why is it interesting that Paranthropus is absent from the Afar? What does that mean for our understanding of human evolution? Okay, so just setting some background. And then because this is a little bit for me as well, I'm really interested in the philosophy of science. So I'll go into the inferential difficulties with inferring a taxon's absence at a given site or region. And then I'll present a model as a solution for kind of overcoming those inferential obstacles. And then, of course, finally, we'll apply the model to Paranthropus and we'll address that question I have in my title, was Paranthropus truly absent in the Afar, or we have just not found it yet there? Okay, so why Paranthropus? Okay, so I probably preaching to the choir, if you will, here, but well, Paranthropus itself, right, for those of you who don't know, maybe I shouldn't assume anything, but Paranthropus is a hominin genus, okay, so ancient human taxon. And I mean, if you look at it, so on the left is what you and I look like without all like the extraneous, soft tissue hair, all that stuff, right? And on the right is a cranium from Paranthropus, and that's a species, Paranthropus boisei. And you could just see how, without being too judgmental, bizarre looking Paranthropus is, right? It's just very hyper specialized. It has all of these awesome adaptations for generating large bite forces. What exactly it was eating is still a bit of an open question. But something that looks like Paranthropus, I mean, we could have never predicted from just studying modern taxa like ourselves and our closest living relatives, the chimpanzees and bonobos. Paranthropus is only something we can know about, in this case, morphologically speaking, from the fossil record. And when I say Paranthropus, I'm specifically talking about Eastern African Paranthropus. Okay, so I'm ignoring South African Paranthropus for now. Okay, so that's just for my talk. And within Eastern African Paranthropus, we have the species Paranthropus aethiopicus, okay, which first appears in the fossil record 2.7 million years ago, disappears about 2.3 million years ago. I'm pretty sure that's up to date, but I could be wrong. And then we have the younger species, Paranthropus boisei, which first appears in the fossil record 2.3 million years ago and disappears 1.2 million years ago. Some researchers think they form a direct ancestor-descendant lineage, a phyletic lineage. Others disagree. Maybe not a surprise considering we're talking about paleoanthropology. Okay, and this is a slide that kind of really introduces why I picked Paranthropus. Okay, so here we have a map of Eastern Africa. Okay, you see we have red points, we have yellow points, and we have green points. Okay, and so what these colors signify is within a site, and hopefully I'm sure most of you know this, there are multiple geologic members and time periods represented, right? And so red means that Paranthropus was never present, i.e. you don't see it in any of the geological members within a site. Yellow is you see it in some, but not all. And green is you see it in all. And usually, and in fact, with these 2 points, I think it's exclusively, it's because they're really only represented by one time period, at least thus far. Okay. And of course, what maybe catches your eye in terms of the red is we have a cluster of red, okay, in this region known as the Afar Depression, right, where we have these 3 tectonic plates that are literally pulling apart. The ground in the middle is sinking, and it forms this depression, which is great for preserving fossils. But of course, interestingly, well, we have many famous hominin taxa from this area, Ardipithecus ramidus, Lucy, Australopithecus afarensis, the earliest member of the genus Homo, right? But we don't have Paranthropus, despite many decades of fieldwork. And so, yeah, that cluster of red there really drives home the conspicuous pattern, which is the topic of my talk. And so, of course, that leads to the question, why isn't Paranthropus found in the Afar? Okay, so that's the pattern. Well, what does that mean for human evolution? Okay, so this is curious because Bernard Wood in 1992 in a couple of papers posed a phylogenetic hypothesis for how hominins are related to each other. And actually, I think Bernard Wood in 1992 was actually at University of Liverpool. So there you go. But okay, so we have a schematic here. Time is on the Y vertical axis, older at the bottom, younger at the top. Okay, I'm sure a lot of us are familiar with that. And here we have a schematic of an ancestor, Australopithecus afarensis. Okay, here typified by the famous Lucy partial skeleton. Okay, so in this paper, Bernard Wood hypothesized that afarensis was the ancestor and gave rise to, on the one hand, the genus Paranthropus, and on the other hand, Homo. Okay, and the question here is, if we focus on the Afar, Australopithecus afarensis is incredibly abundant there, relatively speaking, right? More abundant there than we see at other sites, perhaps especially in terms of early hominins. We just don't see that many hominins at one place. So it's really, really, really striking, right? And as I mentioned earlier briefly, the Afar also is where the Lady Gararjaw was found. So the currently oldest known Homo specimen, mandible, said to belong to our genus, no name assigned. So we have a ton of afarensis, this purported ancestor according to Wood. We have the earliest member of the genus Homo in the Afar Depression, and we have other early Homo fossils, right, like the AL666 palette. But we don't have any Paranthropus fossils, okay? So based on this, you know, if afarensis is truly, or not even truly, it is abundant in the Afar, and if there's really interesting evolutionary action, so to speak, happening there, where branches gives rise to Homo, which we do observe, and Paranthropus, as is hypothesized here, well, maybe this suggests Paranthropus is actually in the Afar, but we just haven't found it yet. Okay, and if we do find it, maybe it lends a little bit more support to this hypothesis that Bernard Wood proposed decades ago. Conversely, okay, we have another more recent hypothesis posed by Josie Jordaens and colleagues that, right, this is Africa, this is the Rift system, this is the Afar Depression. Okay, and what these authors hypothesized is that Australopithecus afarensis was actually most abundant and preferred the habitats and ecosystems on the coastal forest here, fringing the east coast of Africa. Okay, so their big hypothesis was that this was where all the evolutionary action in human evolution was happening. Okay, and what happens here is afarensis evolved into Paranthropus, and thus and migrated inland into the Eastern African Rift system, into all those famous sites where we find it, like the Turkana Basin, okay? But based on this, by migrating inland, it completely bypasses the Afar Depression. So if this hypothesis is true, then we don't expect to find Paranthropus in the Afar. And so not observing Paranthropus in the Afar currently is a real signal according to these authors. Oh, and I should mention a little bit detail if you're interested. They said that I believe it was driven by Milankovitch cycles, but during stable climate times, when you have more forested environments on the East African coast and they migrate inland with these established river systems during stable climate, and hominins just kind of follow that from east going west into the Eastern African Rift. Okay, so we have these two different hypotheses. Wood 1992. Well, let me summarize on this slide. Okay, we have these two evolutionary hypotheses, right? So according to Wood 1992, we have afarensis, proposed ancestor, giving rise to Homo and Paranthropus. Okay, we see a lot of afarensis in the Afar. We see the earliest Homo in the Afar, but no Paranthropus. So that was a phylogenetic hypothesis proposed by Wood in 1992, and then I'm kind of putting words in his mouth here that Paranthropus should be in the Afar according to that phylogenetic hypothesis, but it just hasn't been sampled yet, okay? Jordaens, on the other hand, with their biogeographic hypothesis that afarensis evolved into Paranthropus in the coastal forest, migrated inland into the Eastern African Rift, and bypassed the Afar Depression. Well, the consequence there is that Paranthropus is truly absent from the Afar, okay? So we have these two mutually exclusive hypotheses in the Afar, not sampled yet, truly absent from the Afar. And they imply very different evolutionary scenarios, right? So different hypotheses, imply different evolutionary scenarios, and biogeographic distributions. And so hopefully I've communicated to you by now the importance of distinguishing between these two, that Paranthropus should be in the Afar, but hasn't been sampled yet on the one hand. That Paranthropus is truly in the Afar. Okay, so we can tease apart these different hypotheses. And so that leads me to my main research question. Okay, the reason we have these two competing hypotheses, which are both consistent with the data, is because observed Paranthropus absent from the Afar is consistent with it occupied the Afar, but hasn't been recovered yet, but also with Paranthropus just never occupied the Afar. Okay, and these are mutually exclusive outcomes. Again, the evolutionary and biogeographic implications of which I illustrated with the Wood versus Jordaens et al. And so the question is, well, how do we choose between these mutually exclusive outcomes, right? They're both consistent with the data, with the observed evidence. And that leads to the larger question of how do we demonstrate a taxon's absence? Okay, which leads to the second section of my talk, the problem with inferring a taxon's absence. Okay, so demonstrating a taxon's presence at a site is straightforward, right? All we have to do is discover at least one specimen from the taxon, okay? Simple enough. But demonstrating an absence of a taxon at a site is much, much, much more difficult. Okay, so we could do a little small thought toy experiment, right? So on the left hand, we have the number of non-Paranthropus specimens recovered at a site. So from other taxa like antelope, lion, zebra, et cetera, right? And then on the right, we'll have a conclusion about Paranthropus absence. So if we're digging at a site, okay, let's say we turn up 10 specimens, which again belong to these other taxa besides Paranthropus. What can we say about Paranthropus truly absent being at the site? And by truly absent, I mean never occupy that site during its lifetime. Can we say Paranthropus is truly absent? Well, I hope most of you would agree, no, right? 10 isn't a very large sample size, and particularly if Paranthropus is rare, which we know from the work of, like, for example, René Bobet, hominins are very, very rare, typically on the order of, if I'm remembering correctly, like 0.1% at many sites where hominins are found, okay? Then you wouldn't expect to recover Paranthropus after sampling 10 specimens, okay? So we really have no idea whether Paranthropus is truly absent or not. Okay, fine. What about 100 specimens? Okay, but still Paranthropus is very, very rare. Again, 0.1%. There's a very, very good chance we would just miss it if it wasn't there. Okay, so let's keep sampling. No problem. Well, that's putting it trivially. Field work is very hard. There's a lot of logistics involved, a lot of funding that needs to be secured. But let's say we all do all that and recover 1,000 specimens, okay? You know, there's still a chance, especially at 0.1%, that we would miss it. So truly absent, you know, maybe, maybe not. Okay, now let's go bananas. So 10,000 specimens, okay? But again, we still can't be super confident, or we don't know how confident we are about how truly absent Paranthropus is at a site because, you know, maybe at the site it was actually rarer than 0.1%, right? And then so on and so forth. So we have this unknown quantity truly, for example, the true relative abundance of Paranthropus at a site. If it was 0, then Paranthropus was truly absent. But if it's greater than 0, but just a smidge greater than 0, right, we would need to recover a lot of specimens to have some confidence in saying that Paranthropus is truly absent. But we don't know the true relative abundance, right? It could always be rarer than assumed, and thus we would always need to recover more specimens, okay? And so how confident are we with saying truly absent? I mean, we're more confident as we recover more specimens, but we really don't know. We can't put a number on it, okay? So this slide kind of summarizes everything I went through on that previous slide. So on the left-hand side, in terms of inferring absence of a taxon at a given site, if we don't sample any fossils at the site, right? Let's say we haven't dug there yet, we have no idea whatsoever if Paranthropus is truly absent at the site or not. And as we sample more and more and more, we're more confident Paranthropus is absent, but we really have no idea how much more confident. And the only way we can demonstrate or prove Paranthropus is truly absent at a site is if we sample every single fossil there on the surface in the outcrop, right? Which I hope most of you would agree with me is ludicrous and frankly virtually impossible, okay? So we can never really get here. The question is, where on the spectrum are we? Okay. So, right, the question is, where are we on here? We really currently have no idea, given that we sample, I don't know, X number of specimens, not from Paranthropus out of sight. So it is unclear how to infer a taxon's absence, given that it is currently not found at a site. Okay. Big problem. And again, I hope I've set it up enough with my previous slides that this is an interesting problem worth pursuing. But this is the general problem with inductive inference, right? How do we generalize from our limited sample to the larger unknown? Okay, and anytime anyone learns about inductive inference, it's always the white swan problem. And so if we go around the world and we observe swans, of course, we can't observe every single swan in the world, right? But we observe a subset and they're all white. Can we then make the statement with confidence that all swans are white? Maybe, maybe not. And as we observe more and more swans, we're more and more confident that all swans are white. But how do we know how confident are we? How do we know that there's not some non-white swan lurking out there waiting to be discovered? And would you know that black swans were actually discovered in Australia in 1697? So there you go. And according to this website, blackswanevents.org, this was an unexpected event in scientific history and profoundly changed zoology. Right? So this problem of inductive inference and kind of extrapolating from our current sample to the larger unknown, right? That's a general problem of interest that spans multiple fields of science. It's also best exemplified by, so Bernard Wood was one of my former professors in grad school, and he'd always say, absence of evidence is not evidence of absence. So very trite, but it really exemplifies this problem. Okay, so bringing it back to Paranthropus. So if we haven't found Paranthropus at a given site, how can we generalize and say future specimens will also not be Paranthropus, right? It's exactly the white swan problem. How do we know there's not a black swan out there waiting to be discovered? How do we know Paranthropus isn't out there waiting to be discovered in the Afar, right? We can recover all these wonderful taxa at the site. We can recover hundreds of specimens, thousands of specimens, tens of thousands of specimens. But how can we say how confident we are that Paranthropus was truly absent from the Afar? Well, hopefully from my last set of slides, you can kind of intuit that, well, it is actually impossible to demonstrate or prove a taxon's absence unless we sample every single fossil at a site on the surface in the outcrops below the ground, which of course, I hope you'll agree with me, is a ridiculous proposition. So the best we can do is put probabilities on these two mutually exclusive outcomes I talked about earlier, true absence versus unsampled presence of Paranthropus at a site. That sounds great. But then the question is, how do we actually do this? Okay, so that leads me to my main research question. So observed Paranthropus absence from the Afar is consistent with, okay, so this is a bit of a review. Paranthropus occupy the Afar but hasn't been discovered yet. And Paranthropus never occupied the Afar. It was truly absent there. And so what we want to do is we want to estimate the probability that this is true versus probability that this outcome is true. Okay, so how do we do this? So that leads me to my third section, a model as a solution. Okay, so it's here where I'm going to acknowledge my colleagues. So I started this project towards the end of my postdoc at the University of Chicago, which I did with Zerai Lemseged. And I met there Eric Friedlander, who's a statistician. We met at like a social softball league. And so he helped me a lot to develop the mechanics of this model. And yeah, John Rowan, his knowledge of the fossil rock record is much better than mine. And so he helps me out with that. And I think I just saw him sign on. So there you go, John, that's you. And I think technically you're in an archaeology department, but I'm not quite sure how that works at Cambridge. So I'm just going to leave it as anthropology. Okay, so for calculating the probability of each of these, we need to explicitly model each of these outcomes. Once we do that, then we can calculate the probability that this outcome is true versus the probability that this outcome is true. Okay. And then once we do that, we can actually calculate the probability that Paranthropus was truly absent at a given site. Okay, given that we haven't found it after sampling X number of specimens from other taxa. Okay, and this is exactly the quantity we want to estimate to address the research question that I laid out at various points in my talk and is the title of my talk, right? Was Paranthropus truly absent at the Afar depression? Okay, so how the model works. If Paranthropus was truly absent at a site, okay, its relative abundance there would be 0, right? Which means it would make up 0% of the fossil assemblage. You would recover 0 specimens from Paranthropus, right? Which makes sense because it never occupied that site in the Afar depression. Okay, so that one's straightforward to model, relatively speaking. Now, Paranthropus was present at the site, but may or may not have been sampled yet, possibly unsampled. How do we model that? Okay, so here I just want to do a quick thought experiment again. Imagine we sample 10 mammalian specimens. Okay. If Paranthropus' true relative abundance was 0.5, how many Paranthropus specimens do we expect to recover out of the 10? Okay, so it's not a trick question, right? It's 5. Relative abundance makes up half the assemblage. Then we would expect to sample for half the specimens to be Paranthropus. Okay. And then the probability of sampling Paranthropus, aka that a given specimen that we find belongs to Paranthropus, is also 0.5. And so here I just want to emphasize certain points. So one, Paranthropus presence modeled as relative abundance greater than 0. Okay, because it was there at the site. We just may or may not have sampled it yet. And then this is the frequentist definition of probability for those of you that are familiar with that. But the relative abundance of a taxon at a site is equivalent to its probability of being sampled at that site. Okay. And that is connected to the number of specimens, in this case from Paranthropus, we would expect to sample, given that we sampled some number of total mammalian specimens. Okay, so here we're connecting total number of mammalian specimens sampled, the relative abundance, aka the sampling probability of Paranthropus, and the number of expected specimens to sample. Okay, so these 3 quantities are all worked into the model to model Paranthropus, possibly unsampled presence. Okay. But the problem is we know a taxon's abundance varies across sites. Okay. I think this has been studied by a few researchers. Again, I'm thinking René Bobet's work for the hominin record, but we can also look at taxa that are living today, what we call neo-ecology as opposed to paleoecology, right? So here's a study from Brian McGill. We have the black oak, so this is one species. You can see here the color gradient refers to abundance. So white refers to higher abundance. Black refers to lower abundance or 0 abundance. And this is a map of the eastern US. And so here we have a white outline, okay, which is the geographic range of the black oak. And within it, we see a lot of black, okay, and a few spots of white. And so what this is telling us is that the black oak is common at a few sites, but rare or even absent at most sites. Okay. And again, the absence here could actually also be that black oak was there, but was super rare and hasn't been observed yet. Okay, here's another one, the red-eyed vireo, right? So on the y-axis, we have number of routes, the sampling units, and on the x-axis, we have the number of birds observed per route. And we see that most of these sampling units have very few birds. Okay, so towards the left of the x-axis, number of birds per route, right? And very few routes, so lower on the y-axis, have a lot of birds, okay, towards the right on the x-axis. So again, basically the same exact pattern we see with the black oak. Okay, the red-eyed vireo is common at very few sites, but rare at most sites. And I just put up two examples, but this is one of the few general ecological patterns that we have established in ecology. Okay. So this is very strong. So then this gives us confidence that, okay, Paranthropus probably followed the same pattern in the fossil record where it's common at a very few sites, but rare at most sites. So the takeaway from that is we have to let relative abundance vary across those sites where Paranthropus is inferred to be present, okay? And in fact, we want to capture that pattern where it's rare at most sites and common at a few sites. Excuse me. So here we have a plot. Don't worry, I haven't put up any data or curves yet, but I want to explain the axes. So on the x-axis is Paranthropus relative abundance across sites, okay? Y-axis is probability density, but you could think of this as a histogram. This could be number of sites if that makes it easier for you, okay? And the way we model for relative abundance varying across sites is using something called a beta distribution. Okay, so here we see various iterations of that. We force it to have one parameter, it's usually two parameters. And the reason we do that is because we want it to be monotonically decreasing, right? Just like the red-eyed vireo, we want it to be rare at most sites and common at a few sites, okay? But now the nature of how this curve diminishes is determined by this parameter lambda, and I just put various values to show you how that affects the shape of this one parameter beta distribution. Okay, and the takeaway here is as lambda increases, that curve becomes sharper and sharper. And so that pattern of Paranthropus being very rare at most sites and common at a few sites, that becomes more dramatic as lambda increases. Okay, and with a larger lambda, you would expect to not recover Paranthropus even if it was there, right? Because it's just super, super rare. Yeah, very, very, very rare at most sites and kind of common at a few sites. Okay, so we expect to not even recover it if it was truly present. Okay, so this sounds great on paper, but then the question is, how do we operationalize all this? Okay. And it's not trivial, or at least not trivial with anyone without a formal stats background, which is me. So we have to use probability theory, okay? And so this is the main equation. I don't expect you to understand this at all. I guess part of me is doing this just to show off. But what I want to emphasize is that, so what's going on here is we're modeling that Paranthropus, the number of recovered Paranthropus specimens at a given site, but it's made up of these two components. This one represents Paranthropus true absence. This one represents Paranthropus unsampled presence, okay? So we've basically taken everything I've talked about thus far, these two mutually exclusive outcomes, how do we operationalize them with relative abundance, expected number of Paranthropus specimens, given that we sample this number of total mammalian specimens. Okay, all that is encoded in here and translated into the language of math. And both of these outcomes in red and blue are represented in this model, okay? So we translated the problem into math, which is great, because then we can use maximum likelihood estimation. So it's a way to estimate parameters, to estimate these two parameters in our model. Psi I didn't talk about, but lambda I did, right? That tells you how sharply that curve drops, right? And then we quantify the uncertainty of the parameter estimates. For example, we put confidence intervals on the parameter estimates by bootstrapping the data. Okay, so we can estimate these parameters from the data. But that itself doesn't give us the answer of the probability of Paranthropus true absence at a given site. Okay, given that we haven't found it after sampling however many number of mammalian specimens. So this is step one. Step two is then we need to use Bayes' theorem. Okay, it was Reverend Bayes, or purportedly as a picture of him. And so what we want to do then for each site, we want to compute the posterior probability, okay, or you can just think that's probability, of Paranthropus true absence, which is our main research question, given our parameter estimates, which I showed on the previous slide, and the fact that we haven't found Paranthropus after sampling n specimens. Okay, I've color-coded these phrases because, again, we could translate this statement into math using Bayes' theorem. Okay, So this is the generalized probability notation. We substitute it with the proper distributions. For example, that one parameter beta distribution I talked about earlier. Okay, and it solves to a relatively simple equation. Okay, something that you can solve with, like, I don't know, high school algebra, right? But this is it. Okay, so we have our estimated parameters, right? Estimated from the data using maximum likelihood. This is a number of total mammalian specimens recovered at a site. So all that is encoded in here. Okay, so we can estimate that probability of true absence. And this posterior probability we're calculating for each site, and this is our main quantity of interest. Okay, so let's apply the model to Paranthropus. Okay, so maybe late in the game, but the materials for this study. Okay, there's a total of 56 quote unquote sites between 3 and 1 million years ago. Okay, 37 of which don't have Paranthropus. So this is the same map I showed earlier. I forgot to mention it just encompasses sites between 3 and 1 million years ago. But I'm here to explain why sites are in quotes, because you could probably see here, there are not 56 points on this map, right? So how are we defining sites? Okay, we define it this way. So at Kubifora, a very famous paleontological site, right? There are, again, multiple geological members representing different time periods. Kote, KBS, Upper Bergi. Okay, time is on the vertical axis here. And so what we're doing for this project is treating each member as a different site, okay? So I know site can be ambiguously defined, but this is how we're defining it for this project. So this is what I mean when I say a site. And for each of these sites, we go through the literature and recover the number of Paranthropus specimens recovered. Okay, for some sites it's 0. Observed absence for some sites is greater than 0. And number of total mammalian specimens recovered. Excuse me. So here's a summary of those data. Okay, y-axis number of sites, x-axis number of Paranthropus specimens recovered at those sites. So this is histogram. And again, we see that pattern that I showed you for the black oak, the red-eyed vireo. Most sites have very few or 0 number of Paranthropus specimens. Only a few sites have Paranthropus being very common. And we also do see this reflected in just the total number of large mammalian specimens recovered across sites. So most sites have, relatively speaking, fewer specimens recovered, large mammalian specimens in general, and only a few sites have a lot. Okay. For those of you that are interested in this, it's related like statistical mechanics, but this is log normally distributed, which is interesting. I can go into that more detail for the Q&A if you'd like. Okay, so to summarize the methods, okay, once we collect those data for each site, number of Paranthropus specimens recovered, number of total mammalian specimens recovered, we want to estimate our model parameters using the data. We only have 2 parameters, which is actually really, really impressive given what we're trying to squeeze out of the data, right? I mean, we have this many parameters when we fit like a simple linear regression model to data. And then we want to calculate, after we estimate those model parameters, we want to calculate the posterior probability Paranthropus was truly absent at each site, given the estimated parameters, and the fact that we sampled a certain number of mammalian specimens without finding Paranthropus. Okay, so let's look at the results for this first bullet point. Okay, so this lambda parameter. So setting up the axes for the plot again, x-axis is Paranthropus relative abundance, aka sampling probability, right? Those two are equivalent. Note that this is on the logarithmic scale. And on the y-axis is probability density. Again, if it helps, you can think of that as just like number of sites. Okay, you can think of it as like histogram. But this is what the curve looks like. The lambda parameter estimated is 153. So you may or may not remember from the previous slide when I kind of had the rainbow curves, right? Parameter estimate for lambda of 153 means a really sharply dropped curve. Okay, it just looks this way on when you log transform the x-axis. Another way to communicate this result, which is that Paranthropus is really, really, really rare at most sites, is that 80% of the probability density, aka 80% of the area under this curve, is below 0.01. Okay, so Paranthropus is very, very, very likely to have a relative abundance of less than 0.01 at most sites. Okay, so again, emphasizing that hominins in general, but of course, in this case, Paranthropus, truly, truly rare. Okay, and how well does our model fit, right? If our model fits really well, that gives us confidence in our parameter estimates, which then feeds into that Bayes theorem posterior probability calculation, right? And then in turn gives us confidence about that posterior probability. So here on the, I am sorry, I keep explaining these different orders, but on the y-axis, we have number of sites. On the x-axis, we have number of Paranthropus specimens recovered at those sites. Okay, a line is going to be what is observed. And the gray point is going to be what's expected from our model, the model predictions. And we see that our model fits the data really, really well. Okay, the lines always pretty much match up with the points. So that gives us, again, confidence in our parameter estimates, which in turn gives us confidence in the calculated probability, posterior probability that Paranthropus truly has to set aside, which depends on those parameter estimates. Okay, so now let's go over the second set of results, which address the main question of this talk. Okay, so we want to calculate this posterior probability for those sites without Paranthropus. Posterior probability true absence. Because for those sites where Paranthropus is found, the posterior probability is 0. If Paranthropus is found to be at a site, then the probability that it's truly absent is 0. Okay, so not interesting because it's a trivial result. So these posterior probabilities are most interesting for those sites where Paranthropus isn't found. So this is a terrible way to present results. Just bear with me for a second. I just want to emphasize here that for each site where Paranthropus is not found, okay, we have a calculated posterior probability that Paranthropus is truly absent from the site. And we have corresponding 95% what are known as credible intervals. You can think of them as confidence intervals that are from bootstrapping the data. Okay. And so, yes, we have one of these probabilities for each site. It's a distribution because we have a main estimate. We have some margin of uncertainty. But maybe what you could take away from here is that none of these are above 0.9 in terms of the estimates, right? And these curves or these credible intervals are actually quite wide. Anyway, like as I said, this is a terrible way to present results, so let's do it visually. So for those sites that don't have Paranthropus, again, y-axis probability density, x-axis that main quantity of interest, posterior probability Paranthropus was truly absent, given that we haven't found it after sampling a certain number of mammalian specimens. Okay. In red, I'm going to show you a bunch of distributions. The red ones are the Afar sites. The black ones are other sites. And each of those distributions at a site have a width and uncertainty that's from bootstrapping. So here you go, okay? So some takeaways here. These probabilities are all over the place, okay? If Paranthropus was truly absent from the Afar, we would expect the red curves to be more concentrated on the right. We do not see that here. And in fact, we see very few curves concentrated on the right in general, maybe these 3 sites. But again, none of these sites, their estimated probability, ignoring uncertainty for now, none of them are above 0.9. Okay. So that's not very high. But then the question, of course, is, well, is 0.9 high? Maybe to other people, 0.9 is high enough to say that Paranthropus is truly absent at a site. And so people interpret probabilities differently, right? And that's because we all have certain biases, we all have certain different aims and research questions. And so is 0.9 high depends on your research question of interest and what is your evidentiary standard for saying Paranthropus was truly absent at a site, right? And so I could illustrate this with, if I ask you to take a bet where you have a 90% chance of winning $5, but a 10% chance of losing your life savings. I mean, would you do it? Right? Some people might. They think 90% is quite high. I personally would not, because 10% is not trivial. That's pretty high, okay? And so based on that, I would say 0.9 is not high enough, at least for me. I tend to be fairly conservative scaredy cat, I suppose. to confidently say Paranthropus is truly absent at a site. 0.9 is not high enough. Okay. And on top of that, these distributions are really wide. So there's a lot of uncertainty on this posterior probability of true absence anyway. Okay. So, right. In sum, for the results, posterior probabilities for Afar sites are too low, according to me, for convincing Paranthropus true absence. Maybe you might think differently. That's up to you. Okay. Now, note that I'm not saying Paranthropus was present at these sites. Okay. I just don't say we have enough evidence to say true absence or true presence. And so more field work is needed to distinguish between true presence. That happens when we discover Paranthropus at, for example, an Afar site. And true absence, which as we discover more and more mammalian specimens, that'll increase that probability of true absence. That'll become clear in a bit. So my conclusion of more field work might be really unsatisfying, and you might be rolling your eyes right now because you're like, every paleontology paper I read, the conclusion is we need more field work, we need more fossils, we need more data. That is fair. But there is one contribution we can make. So remember this slide? Okay. On the spectrum, no fossil sample, no idea Paranthropus is present. As we sample more and more fossils, not from Paranthropus, we're more and more confident Paranthropus is truly absent at a site. Okay. But as I emphasized multiple times previously, we have no idea where on the spectrum we are. Okay. Well, our model presents a solution. Okay. So our model can tell us exactly where we are on the spectrum. And this is something what we call an absence sampling curve. Okay, so on the y-axis, we have that posterior probability that Paranthropus is truly absent from a site. Okay, that main quantity of interest. Well, guess what? This is exactly our spectrum. Okay. And on the x-axis, we have number of non-Paranthropus specimens recovered at a site. And so our model can tell us the shape of this relationship, and it looks like this. Okay. So for a given number of specimens that we have recovered at a site that aren't from Paranthropus, we know where we are on this curve, and thus we know where we are now on this spectrum. Okay. And this curve has properties that are intuitive, right? When we don't sample any Paranthropus, our posterior probability is very low. And as we sample more and more, it increases. And this curve tells us how it increases. And this curve is derived from our model. And right, as we sample more and more and more, it limits towards one, but it never truly approaches one, right? Again, the only way we could achieve one is if we sample every single fossil at a site on the surface and underground. Now, to really drive home the nature of this curve, let's log transform the x-axis again. And now let's put some numbers on this. So if we want to achieve 0.5 posterior probability of Paranthropus true absence, we need to recover 13 specimens. No problem. We could do that in field season. Easy. But again, 0.5 is not very high at all. If we want to achieve 0.75, we need 347 specimens. Okay, that's probably pushing it for a field season, but, you know, doable over a couple of field seasons. But 0.75 is not super high. Now, 0.9, right, that number I was talking about multiple times earlier, to achieve that probability of true absence, we need over 1,300 specimens. Now, that is a lot. Nothing to sneeze at. But again, if you work at a site over many, many, many field seasons, you could do it. But 0.9, again, I say not very high. Now, if we want to reach our canonical 0.95, we need over 3,000 specimens. Quite a lot. And if we want to be super, super confident, let's say 0.99 probability of true absence, we need to recover over 16,300 specimens, which is enormous. Okay. And again, this just drives home how rare Paranthropus is, such that we need to recover so many specimens that are not from Paranthropus to confidently say Paranthropus is truly absent. But again, right, what this is illustrating is now we have a way to know where we are on the spectrum, given we sample a certain number of non-Paranthropus specimens. Okay, so in conclusion, our model acknowledges the pitfalls of inductive inference and estimates the probability of Paranthropus true absence. I would say that the Afar sites are not sampled well enough to confidently infer Paranthropus true absence, but the probabilities are there. And if those are high enough for you, well, go for it. And yeah, according to my conclusion, I would say we need more field work to support Jordan's et al.'s 2019 hypothesis. And I think probably the coolest takeaway from our model is that, yeah, our model generates a formalized relationship between the number of mammalian specimens recovered at a site and the probability of Paranthropus true absence, that sampling curve. So now we know where we are on that spectrum of how confident are we that Paranthropus is truly absent at a given site. Okay, thank you.
Thank you, Dr. Du, for a really great talk. I'm sure we'll have a few questions coming up either in the chat or people are welcome to put their hand up and unmute to ask out loud. Just wait a second and see if anyone's typing. Oh, John, would you like to ask a question?
Yeah, sure. Thanks. Yeah, that's really interesting. And I'm sure it's relevant to lots of other species. If you can just first in some way determine how likely they would be, what their frequency would be in a living assemblage. I mean, I couldn't take in all of your equations and so on, but I guess that's a starting point that you usually have to have, whatever the species is. I don't know if you could sort of check that out for me, or but the other thing is, I guess your 56 sites. Well, that's interesting. Um, you were showing Shemaron never present, whereas in the Baringo Basin at Chesawanja, just across the lake, we have two occurrences of Boy's Eye, perhaps a bit later than Shemaron. But there's obviously that interesting possibility that if it's almost within eye shot, if you have it at one, you could have it at the other. While I don't mean to go on, but I also noticed that the final date that you gave was the latest date you gave for them was 1.2 million. And I'd be interested to know which one that was so late. But just coming back to my original point there, am I right then? The whole background to it hangs on how well you can estimate what the frequency of a species would be if it was there.
Oh, so sorry, that was the question. Can you repeat that?
Yeah. I couldn't fully take in your equations, but what I'm reckoning is that it's going to depend on how if it's there, how frequent would an animal be in the landscape. Presumably, you've got to know that if you have a bovid, it might be there at 20% of the whole faunal assemblage, whereas if you have a hominin, who knows, is that going to be 1% or whatever? Presumably, you have to estimate that kind of background.
Yes. So yeah, thank you for your question. Also the comment about, man, now that made me nervous. I was like, yeah, I know Paranthropus at Chesawanja. Did I actually lump it in with a site or did I completely miss it? So it's great that this isn't published yet, so I could double check that. But yeah, the comment that it's in Chesawanja, which I guess I didn't fully appreciate how close it was to Cimarron. So as long as it's not separated by too much time, the Cimarron sites of interest I included and the Chesawanja sites you're referring to. Right, this is one of those things then where, intuition would say it probably was at the Cimarron. We just haven't recovered it yet. And especially, yeah, from the map I showed, I mean, Chesawanja or Cimarron is like an island of red surrounded by yellow and green, right? And so that probably says, you know, we just need to sample more fossils from the Chevron, and I wouldn't be surprised if we eventually find it there. Now to get at your question, and let me know if I'm not answering it, but you're right, especially for modeling Paranthropus presence at a site, possibly unsampled presence, we need to have some idea of how common it is, right? And so that is illustrated by that beta distribution curve where I showed 80% of the density is below 0.01. But then how do we actually estimate that, right? And so one of the nice things about this type of model, it belongs to this general class of models known as like hierarchical modeling, multi-level modeling, is it does something called borrowing strength. And so from those sites where Paranthropus is actually present in the data set, right, the model is drawing that information and using that to estimate this distribution of relative abundances across sites. And so the reason it's called borrowing strength is because the inference and the estimated parameters in the model, and let's say if we want to focus on inference at a given site, it's actually drawing information and almost like power from information from other sites. I don't know if that answers your question.
Well, I think so, certainly as far as I can understand. So thank you very much for, you know, it's been a really clear presentation and very, very thought-provoking, actually. Thank you.
Yeah, thank you. And also, yeah, Bernard Wood speaks very highly of you. So it's nice to virtually meet you, John.
Okay, right. Yes, thank you.
Thank you, John, and thank you, Andrew, for your answer. Marta, do you have a question?
Actually, it's Rob Foley sitting here who has a question.
I don't have my own computer. Thank you.
But I can say thank you, Andrew, for the talk.
No, thank you. It's very, very stimulating. And I mean, I think you're
John is saying hello.
Oh, hi, John. No, I was just thinking that you know what's obviously the great strength is that we do need more models that set up expectations against which we can compare the observed, and I think that's very promising. My question is how much the models are influenced by the diversity of the assemblages. So, for example, if you have an assemblage of 10,000 and they're all hippopotamus, it strikes me you'd get a very different set of probabilities than if you've got an assemblage which has, I don't know, the whole range of antelopes and buffaloes and things in there, and how this would influence the results.
And I have to add just in there an add-on how the model is influenced by the presence of another hominin.
Okay, so I will take these questions one at a time. These days, my attention span is so short. So, Marta, you might have to repeat your question later.
Okay.
But Rob, what was it? Oh yeah, hippopotamus versus diversity. That's interesting. So, is the implication that because if a site is all hippopotamus, you would be less likely Paranthropus would be less likely to be there than in like a diverse assemblage that might sample a diverse swath of like habitats, ecological settings. Is that the implication?
Yeah, I mean that's the ecological implication. I mean the statistical implication is your probability curve is it's the sum of all the curves of all the different species. So the question is if there are many variable curves in there, you could have to. I mean, it could work. I think most assemblies have some diversity, and the question is whether you can use the variation in those curves to leverage a bit more power out of it. That would be the positive approach. The negative approach would be to say, well, unless we knew the ratios of different taxa, it would be very difficult to do it.
Yeah, so explicitly the data and how the model is modeling the data. I mean, well, it's agnostic to diversity and it's not considering those curves and summing up those curves, but implicitly, is that what's kind of going on underneath the hood, so to speak? And how does that affect the results? Wow. Um, Honestly, I've never considered that. To give you a satisfactory answer, I have to think more deeply on
To
that.
think about
Think
things
think
to
about it.
think about.
You know, these
Okay.
these are it's a you've set up an interesting problem, and of course because it's relatively novel, you know, there are always going to be new challenges as you progress. So it's just a thought that I had. Anyway, thank you.
Yeah, I appreciate that. Thank you. Oh, Marta, yeah, sorry. What was your question again?
So so my question was, it's similar, but specific in hominins, whether the presence of hominin at a site
Hmm.
increases the probability that I will find another hominin. So forget Paranthropus for a minute, and do sites with a hominin. I know Nyayanga has only one tooth, but do the majority of sites with hominins are more likely to yield other hominins than sites without? There's a
Yeah.
sort of a combined of taphonomy and ecology and paleoecology, and can we then leverage in the model, you know, all those sites with Afarensis or Homo in the Afar, the fact that there are hominins there, would that increase or decrease the probability of finding Paranthropus?
Yeah, so I guess my answer can be similar to Rob's in the sense that I mean obviously that was not explicitly modeled, and so the question is that implicitly in the model somehow? I guess I could see it go both ways where I mean my intuition is that if a hominin is found at a site, then you're more likely to find another hominin taxon because of preservational circumstances, you know,
That's the
phylogenetically,
taphonomy side, right? And the
right,
ecological side, there's the other. The hominids could be competing with each other, and there
right,
is niche
right.
exclusion. And the South
Yes.
African caves with a hominin per cave, except particular circumstances and so on. So it's also thinking of both taphonomically and ecologically, they could be acting in tension, but there will be
Yes.
interesting things to consider.
Right. But also ecologically, I mean, because they're phylogenetically similar in terms of the scope of all animals found at a site, one would you know, their ecological preferences, if you will, could be quite similar. But again, that's a scale dependent thing. You know, if you're focusing on all mammals, but focusing on just two hominins, then yes, they could be different. So I guess a way I could generally, so it could go either way. So probably not a straightforward relationship, although that would be interesting to explore. That's a separate
Yeah,
question, but
there's
probably separate analyses.
interesting
But
questions to add. Yeah.
yes, but I think a general way to answer your question and Rob's question is that you know, I modeled relative abundance, aka sampling probability Paranthropus across sites with that one curve, right? The one parameter monotonically decreasing beta distribution. Now, there are a lot of things that influence relative abundance, aka sampling probability, right? There's ecological stuff, which we touched upon. There's taphonomic stuff. And so all of these different processes, I mean, there are so many such that, I mean, it would be very difficult to model in any satisfactory way. But what that does is if all those processes act in all different directions, and one we just talked about where a presence of a hominin, it could be taphonomically and maybe ecologically that presence of one hominin taxa means you're more likely to find another one, but it could also be ecologically opposite, right? Yeah, it'd be competitive exclusion. So if all of these processes are going in every which direction, pushing it relative abundance higher at a site or maybe lower at a site, then what that ultimately does is create noise. And so that's kind of subsumed in that distribution of the relative abundance across sites, where that you could think of almost like the super variable, right? That's being influenced at smaller scales by all these different processes that I just mentioned. And all these smaller processes are combining together to form this emergent distribution whose variation is kind of incorporating all of this. So it's almost like this relative abundance and sampling probability curve is modeling, incorporating all this stuff at a larger scale. And so maybe that's what I was trying to get at in terms of this model is not explicitly, but maybe implicitly taking care of a lot of this stuff.
Okay.
Hopefully that
Thank
was a
you,
satisfactory
Andrew.
answer. Yeah. Yeah. Good
Thank
seeing you
you.
too.
Okay, I think it has just gone 5, but Matt put his hand up before 5. So, Matt, do you want to ask your question? That'll be the last one that we have time for, I think.
Yeah, sorry for keeping you beyond the hour, Andrew, but this is really fascinating. And I think it's great that you can actually put numbers or probabilities to these things. I think it's absolutely brilliant. My question, in a sense, is kind of an adjunct to Rob's, and I think Rob kind of hit on something that was floating around in the back of my head, which is when you were setting this up, I thought you were going to go in the direction of species area curves or species sample curves. And I guess in a sense, the beta is the inverse of that. But I wonder if you could do that as an adjunct because it would tell you about generic diversity and its relationship with the size of the sample. Because my suspicion again would be that if that curve hits an earlier asymptote, it would increase your confidence that you weren't going to find an additional species, whether it was a hominin or not. So I wonder if that would be a possibility again in the kind of direction that Marta and Rob have suggested.
Yeah, that's another very interesting comment. Man, these are great questions. Right. So species area curve, um, as you recover more individuals, you recover more species, takes that into account the spatial autocorrelation of the individuals. And if you recover more species, you're more likely to recover Paranthropus. I think that might be the logic of what you were getting at. Yeah, I mean, I would say that, I mean, that's very interesting. I mean, my intuition is that might be a more indirect way of getting at this question of Paranthropus true absence. Um, and again, I guess this theme keeps coming up of explicit versus implicit. I mean, because at a site area is kind of fixed, but maybe individuals, number of specimens recovered, I mean, that's a function of many, many things, but one could be the amount of time represented at a site. And so if a site is more time average, all else being equal, you're going to recover more specimens. So there we have species time curve. Okay, the temporal analog, the species area relationship, species time relationship. And so if you recover more specimens, you're more likely to recover Paranthropus if it was truly there. And I mean, that statement and that sentiment is captured in that absence sampling curve, right? The more individuals you sample, you're more confident it's absent. And if Paranthropus is truly there, then the more individuals you sample, not from Paranthropus, you're more likely to recover. And if you recover it, then the probability of true absence drops to 0, right? But if we keep recovering without sampling Paranthropus, then, you know, we could be pretty confident that Paranthropus is truly, truly absent at the site, which of course translates to a high posterior probability of true absence.
Yeah.
I'm not sure if I answered your question, but
Yeah, no, absolutely. I think I think as you say, your approach is more direct. I'm just thinking of that background issue of if, as Rob suggested, if the sample is relatively homogeneous in terms of the other species, perhaps it does make it less likely that you're going to recover something which you haven't already found.
Yeah,
But even if it is as stable as diverse, so we were this summer looking at the bovid, actually the ungulate composition of multiple sites, and you know there was a little bit of taxon specific change, but the categories or the body size categories of bovid, they were all there, and there were about 15 species of bovids every time with slight variations. So it's also the diversity of animals. I think it tells you a little bit about, have I captured that community? And if you get a sense that you've captured the community, the chances that you're missing really one whole element of it are reduced. So I do think that the diversity, the taxic diversity matters as well. It's so interesting.
Yeah, that is interesting. I also want to comment that I don't think I've ever been in a paleontological community where we mention things like species area curves. And so this is a lot of fun because I mean that's the stuff I really enjoy as well. And I know Rob's been interested in that stuff. I've definitely read a lot of his work. Yeah, right. So if you recover a certain amount of diversity, of course, there's a similar problem where you don't know how diverse the true community is, but you can get some idea through things like rarefaction curves, which is ultimately a function of species abundance distributions. And if it's more diverse, then it's more likely that Paranthropus there. Yeah, I mean, this is something I never really thought about in connection with this model. So, like I told Rob, yeah,
Many,
I'd have to think about it more, but this is very
many,
thought-provoking.
a lot of fun, a lot of fun.
Yeah,
Thank you, Andrew.
thank you. Thank you
Narrator
all.
wants to end the session.
I probably should, yeah. Thank you everyone for your participation or your comments and questions. I'd just like to say thank you again to Andrew for, yeah, really great talk. So yeah,
Thank
thanks
you.
everyone. Bye.
Bye.
Goodbye.
Nice meeting you all.
You too.